Before we get into our more complex devices such as our diodes and transistors, we want to start talking about our semiconductor materials so that we can get an understanding of how these devices are working on a subatomic level. So, of course, you might recall from physics and chemistry classes what a semiconductor is. We can classify materials as either conductors, insulators, or semiconductors. And so, of course, semiconductors, as the name implies, kind of falls in between our conductors and our insulators, and we can quantify that in terms of conductivity. For our introduction here, we're going to start by talking about something called an intrinsic semiconductor. And so when I say intrinsic, essentially what I mean is we just have a pure semiconductor. We don't have any defects or contamination. And so we're going to come back in a later video and we're going to talk about sort of the dual of this, an extrinsic semiconductor, where we no longer have this pure semiconductor. So there are different types of semiconductors. The most common one is silicon, and so that's what we're going to focus on, but of course realize that there are other materials that these same ideas apply to. So our most common semiconductor is silicon, and I'll just use the atomic symbol Si. And so of course I've got a periodic table down here, so we can see our silicon is right here. And so typically when we're talking about semiconductors and in the frame of electronics, we'll label our groups as group 4 is where our silicon is. And then on either side of that, we'll have our group 3, for instance, our group 2 over here, our group 5, our group 6, and our group 7. And so I'll come back to that in a minute, but essentially what that is referring to is the number of valence electrons. So again, we're going to focus on our silicon, but just to briefly mention, we can have different types. I want to mention what some of those are. So first of all, let's sort of give a breakdown of two general types. We can have either an elemental semiconductor, which is what silicon is. So elemental semiconductor, and so examples of this would be we are focusing on silicon, so it's just one element. We can have other materials from this group 4, and so we'll see why that is here in a little bit. So an example would be we could also have germanium, and so that was used earlier on, and it's used in certain specialty devices. Another interesting one here is carbon. So we could have a semiconductor that is pure carbon, and so there are different forms based on the carbon bonding, but one sort of interesting subset, at least I think is interesting, is diamond. So diamond is actually one potential semiconductor that could be used in certain applications, and if you look into that more, you'll see things such as wide band gap semiconductors, and it has some specific applications. So sort of the dual of our elemental semiconductor is a compound semiconductor. And so our compound semiconductor, we're taking more than one element and we're combining them to make our semiconductor material. So there are pros and cons of both of these. We're not going to get into our compound semiconductors or the advantages and disadvantages, but again, just to give you a couple different examples of some of our compound semiconductors, we can have two elements both from this group 4. So for example, we could have carbon and silicon. So that's a pretty common one. So that's silicon carbide, SiC. And so that would be what we would call a 4-4. So two group 4 elements. And apologize for my sort of sloppy handwriting there. So those are Roman numerals. So we've got silicon carbide. We could also have, for instance, group 3-5. And so again, we'll come back and we'll talk about our valence electrons, but that's how we're determining how these are paired. But for instance, we could take from group 3 something like aluminum and combine that with something like phosphorus from group 5, and that would give us aluminum phosphide, so AlP. We could also do group 2 and group 6, for instance, and an example of something from that would maybe be cadmium from group 2 and tellurium from group 6. And so this would be cadmium telluride. And so we can't just choose, of course, any element from these. These are specific compound semiconductors that are used in certain applications. And again, there's advantages and disadvantages to elemental versus compound and different materials within each one. Of course, we could spend a whole course just on that. But fortunately for you guys, we aren't going to. But again, we're just going to spend most of our time focusing on silicon. So let's then consider an individual silicon atom. So consider a silicon atom. And so we know from chemistry and or physics that our silicon atom is going to have 14 electrons in total. And we're not going to be worried about all of those, but we could go back and we could say we have so many in the 1s orbital, the 1p, the 2p, all of that stuff. But what we're really going to be concerned with is we know that we have 4 valence electrons. And so by 4 valence electrons, of course, again from chemistry or physics, you might remember that this is basically outer shell electrons. And so that's why we labeled this as group 4 up here, because these elements in this row, or sorry, this column, have 4 valence electrons. So we can draw this pictorially. If we say here's our silicon atom, we can represent each of our valence electrons as a dashed line like this. So these lines represent our 4 valence electrons. Well, what can happen is that this silicon atom can form covalent bonds. So covalent bonds is, of course, where we're sharing our electrons. And so oftentimes I'm going to abbreviate electrons as E with a superscript of minus. So we can share our electrons with covalent bonds. And of course, we're going to share that with our 4 nearest neighbors because we have 4 of those valence electrons. And so we end up with something that looks like this. So we have a silicon atom here with our 4 valence electrons. So maybe we have one right here as well. So that also has 4 valence electrons. And here, where we have the 2 adjacent, we're going to sort of represent it like that. So I can sort of expand this, put silicon atoms on each side. And so you'll notice that once we combine all of these, once we put these silicon atoms sort of next to each other, what we're getting is we can see, for instance, if we look, let me do one more sort of layer here. Okay, last one. So what we get is, if we look sort of at this middle one here, we notice that it has 8 electrons in its outer shell, which is of course what elements want and compounds want to be stable. So if we keep combining enough silicon atoms, we get a single crystal silicon. So silicon crystal, if we have enough of these silicon atoms. And so of course what I have here is sort of a modified Lewis diagram structure. So typically with Lewis diagrams we use little dots, but in microelectronics we'll often use these lines. Of course our silicon crystal is not going to be a planar structure like this, but actually it's going to look something more like this. So we're going to have some type of diamond crystal lattice, it's called. So this is a diamond crystal lattice, and so different types of semiconductors will have different bonding formations, but basically we can see here that this is a tetrahedral bonding formation. So again, this is one of those things that we could spend a lot of time talking about, but I want you guys to just be aware that it's not actually just a planar structure. So one sort of natural question is, what happens when we get to the edges here? So of course, if we have a good sized silicon wafer or silicon crystal, it's going to be very large, but at some point we are going to come to the edge and we're going to have what's called these dangling bonds. And so if we want to do sort of more detailed analysis, we would have to account for these bonds. And unless we're in vacuum, we're going to have something that is going to bond with that. So even if it's just in the atmosphere, we're going to have, for instance, hydrogen and oxygen and water, all these different things, nitrogen that can bond with that. But for our purposes, we're going to ignore these dangling bonds and we're going to say it's negligible. Our silicon wafer is big enough. We're just considering bulk effects. But just be aware that as our devices get smaller and smaller, we can't neglect that as much anymore. So that's sort of our basic introduction in terms of the structure. What we're going to talk about in the next several videos is how this structure transforms into electrons being free and moving about, and ultimately how that turns into current. And then we can look at how our current and voltage characteristics behave when we have certain configurations of our semiconductor material.